Hello, everyone, and welcome back to our flipped classroom in chemistry, where we're continuing to develop our understanding of the atom. So we began with Dalton, who had developed his atomic theory and said that atoms were indivisible. Now we progressed to Thomson, who discovered the existence of the electron and posited that there were negatively charged electrons embedded in a positive atom, so that we had a neutral atom. And we continued through Rutherford, who discovered that the positive charge of the atom was concentrated in one tiny spot called the nucleus. And so now we're continuing to try and understand what's going on with the atom. And so our understanding of the atom evolves as we understand light. So we're going to talk about light and how that led to the development of the next two theories, both Bohr's model and our current quantum mechanical model. So let's talk about light. So light is a tiny, tiny piece of the electromagnetic spectrum. So you can see here in the center of the electromagnetic spectrum, we have our visible light. And the electromagnetic spectrum is these waves that propagate through space at the speed of light. And so it goes all the way down to really large waves down here in the radio frequency, to somewhat larger waves in the microwave frequency, all the way up to tiny, tiny waves in the gamma ray frequency. And the frequency that we can see is here in the middle where we have visible light. So as I said, electromagnetic radiation is waves propagating through space, moving at the speed of light. And so we have an equation that's important here, and that is c, which is the speed of light, is equal to nu, which is the frequency, which is in units of hertz or 1/seconds, and lambda, which is the wavelength in meters. So the speed of light is equal to the frequency times the wavelength. So frequency is how many times a peak passes a certain point in units of time. And so in our case, it's per second. So how many waves are there per second? And then the wavelength is the distance from peak to peak. And again, we're going to measure that in meters. Since this is equal to a constant, the speed of light is a constant. Since the frequency times the wavelength equals a constant, as frequency increases, as we have more waves per second, the wavelength decreases. So again, as frequency increases, wavelength decreases. Okay, so why is all of this important? Well, one of the first observations that led us to think about light as carrying energy is this thing called the photoelectric effect. And what the photoelectric effect is that when light shines on metal, that metal will actually eject electrons. But if the frequency is below a minimum frequency, electrons aren't going to get emitted no matter how intense the light is. So we can make it brighter and stronger, but it's still not going to emit light if it doesn't have a certain frequency. And so from this idea, we come up with the particle nature of light. And we say that the energy of a photon, the amount of energy that one particle of light is carrying, is equal to h, which is Planck's constant, times the frequency. So this is Planck, and he comes up with the idea that light energy can only exist in quantized form. So we have little discrete packets of light, little particles of light, and each of those particles has a particular energy. And that energy is directly proportional to the frequency of the radiation. And here's our equation again. E, or energy, is equal to Planck's constant, h, times nu, which is our frequency. Remember, frequency. And so if we go back to the photoelectric effect, the reason that light doesn't always eject an electron is that this red light with a low frequency doesn't have enough energy to knock that electron off. So we need a certain amount of energy to knock the electron off. This shows us that light of different frequencies has different energies. And we express that with this equation. So as frequency increases, since this is a direct relationship, as frequency increases, energy increases. So again, as frequency increases, energy increases as well. Now, since we know that as frequency increases, wavelength decreases, we know that a long wavelength would equal a low frequency, and that would mean it's a low energy. And so our red light has a long wavelength, has a low energy. But we move up to blue and purple light, they have short wavelengths. That means they have a higher frequency, which means they have a higher energy. So let's jump back to that very first slide here, and let's take a look at our electromagnetic spectrum. So down here in the red end, we have the longer wavelengths, and up here in the blue and purple end, we have shorter wavelengths and higher frequencies. So that means that we can actually predict the energy of our light just by its color. So rainbow order, red, orange, yellow, green, blue, violet, is increasing energy. So red is our lowest energy wavelengths of the visible light spectrum. Purple is our highest energy waves of our visible light spectrum. So from this, we recognize that most subatomic particles, like light, behave as particles but obey the physics of waves. And so we've discovered that we can learn a lot about the subatomic particles from light. So one of the things that we've talked about when we talked about our periodic table is the idea of neon signs. So neon signs truly are filled with neon gas, or at least the original ones were. When the electricity is turned off, the gas is totally colorless. But when the electricity is turned on, electricity excites the electrons. And when it excites the electrons, they jump up to higher energy levels. And they can't stay there because that would require continuous energy. So when they fall back down to their original levels, they give off that energy in the form of light. And so we can determine how much energy it takes to change levels by observing that light. So this is Bohr's experiment. We have the light source, the excited elements, and we pass the light through these focusing slits and then through a prism. You guys have probably seen prisms before. They split the light into its different wavelengths, and we have the detector looking at what the results would see. And so those wavelengths of emitted light are different for each element. Even if we have green and yellow and purple in this two different elements, they're going to be slightly different greens, slightly different purples with different wavelengths. And so they're giving off a different spectrum. So these are the spectra that we see for hydrogen. And all the ones in red are outside of visible light, but these ones in the middle, these are the ones that we can see. So when you excite a hydrogen atom or a group of hydrogen atoms, it gives off all of these colors of light with definite wavelengths. And those definite wavelengths tell us about the energy changes between the levels in which the electron is allowed to exist. So these definite wavelengths correspond to frequencies, correspond to energies, and those energies tell us what the energy levels of the atom are. So the electron behaves as both a particle, as described by J.J. Thomson with his cathode ray experiment, and as a wave, as described by his son, George Thomson, who says the electron is an energy wave. And in reality, it is both. It is both a particle and a wave. So one of the things we can do to identify elements is to excite them in some way, either by passing electricity through them or simply by heating them. And so we can heat different elements in a flame and they will give off a characteristic light. We can look at the spectrum that they give off and we can use that to identify those elements. And we will actually do that in a lab in class. And so you can see that the different elements give off different colors. Okay, that's it for atoms and energy in the electromagnetic spectrum. As always, if you have any questions, let me know and I'll see you in class.